Hey, this lab's going to be dealing with cold working, and I'm going to try and keep the theory portion short because you guys are going to realize there's a lot of steps to the lab. Now, the video is kind of long. I tried to keep it as short. Usually I try and do 15 minutes, and I know it got to about 30 minutes on the lab prep. There's a lot of steps in there, and we're going to help you out in lab where you can accomplish that easily in the 2 hour time. But watch that video, really learn what you're going to be doing with the equipment, and kind of get the gist of what's going to happen. Now, let's talk about this concept of cold working. Now, the first thing we need to do is talk about what is hot working. So hot rolling of steel is done at a temperature above the recrystallization temperature. You notice the steel is very hot, so if we take rollers, it's going to be easier to work because it's hot, as well as the grains are going to regrow. Now we can look at this by the fact that recrystallization means that we take this larger piece, and these are grains. We're going to etch and look at these kind of grains. We are going to have rollers. Now, they're not as big as the rollers we would need for cold rolling because this material is easier to work, and it's going to squash down these grains. And so when we talk about looking at how the grains are squashed and we want to look at them in the structure, we want to look at how it was loaded and cut our samples and make sure we're capturing that loading direction. As the temperature is still hot enough, it will let some recrystallization grow, and we're going to see equax and equax crystals on each side. So that's basically some new grains regrowing, and we're going to basically erase what we did in that hot working operation. One of the things I want to point about hot working steels is basically that the steels are going to be have an oxide out here. Now, that's an oxide scale. If you bend that material, it'll flake off. It's kind of a nasty looking steel. And a lot of times the corners are not as pronounced and square as a cold work steel. This is going to be the majority of our steels that we go out and buy are going to be hot rolled. So lower tolerances, not as much definition on the corners, and you're going to have mill scale. Now, we could order that pickled and oiled and have that mill scale removed, or we could shot peen it. Now, cold working, on the other hand, is we're going to do this at a temperature that's could be at room temperature. We're going to have big, massive machines, mill stands and stuff to come in there and roll that metal down and squash it. And so if we're looking at the grains in that material, it may have started off nice looking, and then it's going to be somewhat deformed. Now, this was heavily cold worked here. And so we have terms, isotropic, meaning the properties would be all the same in all directions. So we really don't have to worry about the loading directions or how this was made. But cold working, the properties in the X and Y directions here are going to be different. We call that anisotropic. And so when we cold work a material, the tensile, the yield, the material is going to have improved properties over the cold rolled. So we can order, for example, 1018 steel hot rolled or 1018 cold rolled, and we're going to see some property changes, as well as the surface finish is not going to have that mill scale, and it's going to have more defined corners and hold tighter tolerances to the nominal dimension that you want. Now, cold steels here are going to have a little bit better corners. We're going to have some steel for you in the lab to look at, and it's mill free. Now then, when we go into lab, we're going to have to take some brass samples, and we're going to cold work them at different intervals of force and see the amounts of cold work we have on that. And cold work is calculated by the percent change over the original change times 100, and that's going to give us our cold work value. We'll probably have some of that stuff on your lab sheets. Now, when we look at this, we're going to see the sample crystals on this. When we take a sample, we're going to cut it, and what we're going to have to do is polish and etch it and look at the grains. And we're going to have different microscope powers that we can look at the grains closer or further off. Now, we're not going to go to the point where we're going to use like an electron microscope or anything, and we're not going to see the actual individual atoms in the crystalline structure. Each grain is a crystal of repeating structures. So you're going to remember terms like body centered cubic, face centered cubic, and all that, and that's making up these grains that we're going to see. This lab, we're not so much interested in the composition of the grains, we're looking at the size of the grains. Now, how are we going to look at these grains? We're going to cut them off on a metallurgical saw. We're going to mount our samples in a puck, a bakelite puck. That's a phenolic material. We're going to put our sample in there, put the powder in there. It's going to heat up, and basically it's going to give us this puck. And then the puck is going to go into a machine that we can grind, so you'll have some grinding operations, and then polishing, and the part's going to come out looking very much like a mirror. We're going to micro polish this at the last stage with an oxide polishing compound. And then we're going to take some acids. Now, this is a still part, and they use nitrile, but you guys are going to use the correct acids, and we'll show you how to do that in the lab as well in the lab prep video for matching the acids with your materials that you want to see. What I wanted to point out here is in the videos, you'll probably hear me talking about getting cloudy or changing in luster. This is something where we rub the acid on just in this portion to kind of show you that it's a big difference. So I can see the acid ate this area out. It ate the grain boundaries and some of the different structures in the material. And when I put it on the microscope, I'm going to be able to see that. Now, it's probably not going to be as dark of a frost. This is a little heavier etch, but maybe I can come out here and get a good image of that sample there. Now, once we have those samples done in a microscope where we can talk about how the grain sizes are going to be, we're going to be able to come in here with a microscope, and we'll be talking about the software where we can look at it in the microscope. We're going to talk about matching the lens powers with what's on the microscope so that we can take measurements, and then we're going to talk about how to capture that and save it to your flash drive. Now, part of this lab, you guys are going to have to be doing grain size analysis. How big are the grains within the metal when we look at it on the microscope? And there's an ASTM standard E112 that deals with this. And so we have a scale of 1 to 10, so larger grains versus smaller grains. Why would we even care about the grain size? Well, the larger the grain versus the smaller the grain, the properties are going to change. Smaller grains are probably going to have higher properties than larger grain. So if we anneal or just do a recovery type anneal, we can see different grain sizes, or even if we cold work, it may change the grain size. So we're very interested in understanding that grain size. Now, what are we talking about grain size? Whenever we have a liquid metal and it starts to solidify, it's going to start a crystal and it's going to start growing and basically extending out till the crystal of one hits the other grain of the crystal of the other, and that is going to form a grain, and where the grains come together, that's going to be our grain boundary. So we can see our grains here in this material. You can see them kind of changing over here in this cool little animation. Now we're going to be going onto a microscope, and we're going to be matching our powers of the microscope with the computer. So we're going to have to make sure the computer and the microscope match up so that we can measure lines across that grain. And what we're going to be able to do is take several lines, draw them, and count the grains within that line. And you're going to save these to your drive as well. Now this is an example of a captured image right here. So let's say that we were on the computer, and we're going to talk about making sure you have the little scale on there and all the images you capture. And we're going to be able to come in here and understand that this is so many microns, okay? And what I'm going to do is come in here and draw a square on this, okay? Now, you may have to do this in Microsoft Paint by using this line as a reference and drawing a square. Now, this test area that we're going to draw right here, I drew twice as long as this line, so this is a 200 micro long line in here. So I have a square that in terms of millimeters is going to be 0.04 squared. So that's the squared area of this. That's my test area, and then I'm going to come in here and count these grains. Now what counts as a grain? If I was in here, I could say, hey, this is definitely a full grain. See, there's a full grain. But you know, like this line right here cuts this grain. So if I only see a grain, maybe that would have been a half because we would have seen others. Yeah, here's that other half. So this is a half a grain. This is a grain. What you're going to do is count the grains, maybe do it again, do it 2 or 3 times, take the average, and I'm going to say that I've got like 20.5 grains within that area. Now, in that standard, they like to say the number of grains, they're going to have this equation, the number of grains is equal to 2 to the power up here of n minus 1. The little n is the grain size number. And what we're going to be able to do is using the number of grains that we just counted, we can solve for the little n here. Now the standard requires us to do it at 1 inch square. That's not going to happen because we're going to be taking an image on our microscope. We're going to draw a square and we're going to have to prorate it for the size so we can correctly analyze how many grains per square inch. So 1 inch is going to equal to 25.4 millimeters. We have 1 inch at 100 power is going to be 0.254 millimeters. So our actual area that we should be measuring is this instead of the area that we had. So we're going to have to prorate those grains in terms of the actual size compared to what the standard says. Now let's talk about calculating this grain size. We have the equation n is equal to our test area of grains. Now this is on that 1 inch square, and so we're going to have that test area versus the standard, which we came here and did. So you guys are going to have your test area that you actually used. This is going to do your ratioing for you. The number of grains in that test area that you calculated. Okay, so we calculated 20.5. We're going to take our ratios here, and the n is going to come out to 33. So n is now 33 grains for that prorated size. We need to solve for the little n. So we talked about, here's that equation that the ASTM standard says, and we need to solve for little n. Now that's a lot of math, and I'm not going to make you guys do that. I'm going to go ahead and give you the equivalent to what n is going to be equal to, and this is our new equation that we need to work with. So we're going to drop that n into here, and when we do that, we're going to end up with 6.04 for little n. Now what is that? That's our grain size. It's a 6 basically grain size. Now, we know our grain size number for that. Another thing that we're going to have you guys do is come in and draw some lines. Another method is to draw lines on the system. So we might draw a series of lines, and what we're going to do is come in there and count the number of grains intercepted or crossed by that line. And so you're going to come in here, and maybe our first line, I count 7 grains. 1, 2, 3, 4, 5, 6, and 7. I'm going to record that. I'm going to come down here and count those grains. You're going to do this several times, take the average, and maybe I'm going to have 7.5 grains on the average. And what I can do is take the 300 micron. Okay, now what is 300 micron? That's the length of the line I had, so that's why we had the nose piece matching the lens power, so we can draw a line across there and it will tell you how long that line is. And then we're going to take our 7.5, the grains we counted here, divide it into that, and it is going to give us 40 micrometers. Now, this is also 0.04 millimeters, or here we have an inch setting of basically 1.5 thousandths of an inch, and that's our average grain diameter. So we can kind of estimate the average size of one grain. Now, once we have those two in ASTM E11, let's kind of tie these two things together, because we did the square area and got our number, our grain size number. We did the 3-line method, and we were actually to calculate the average grain diameter, right? And so we calculated roughly about a 6 on our grain size. And if I come over here and let's look back at this, we talked about a 0.04 millimeter. So our average grain diameter is right here, okay? And if I come down here, I'm at 0.044. So these two methods both kind of get pretty close to each other, and so I feel pretty good in my results in how I established my grain size number and my average grain diameter.